Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll start a new chapter called Simple Harmonic Motion. Simple harmonic motion is a very special type of motion, and before going into the details, I'll give you some examples to see what we'll be talking about. The classic example which is given is that of a simple pendulum, in which I have a rope, light rope, and a heavy bob is attached to it. If I pull this bob towards one side and then release it, it will move towards the center and then it will reach the center, but it will still have a speed towards the left, so it will actually move on to the other extreme, and then it will move back towards the center and to this extreme. And if there is no air friction or if there is no air drag, then this process will go on forever. Another example would be if I have a spring attached to a wall. Let's say this is the natural length of the spring and I have an object attached to it. I could either extend or compress the spring. Let's go with extension. I extend the spring towards the right by pulling the object, and then this length of the spring increases. So the object comes here, the length of the spring increases, it will start pulling the object towards itself. As soon as I release the object, it will move towards the center and the spring will continue pulling it towards itself, so the speed will keep on increasing. Once it reaches the center, the force due to the spring on it will be 0, but it still has a speed towards the left. So it's similar to this case, it will continue moving towards the left, but by this time the spring starts pushing it towards the right because it's being compressed. So it will move to the other extreme, it will come to rest, and then it will move to the center, and this process will go on ideally forever if there was no friction. These are examples of what is called periodic, or it's sometimes called harmonic motion. And periodic or harmonic motion is any motion that is repeated after regular time intervals. So if a bob is moving to and fro in a pendulum, or if an object is moving from one extreme to the other, the motion is repeated after regular time intervals, and so that kind of motion is called periodic or harmonic motion. The time after which it is repeated is called the time period of that particular periodic or harmonic motion. So if I extend this bob and leave it from this end at t is equal to 0 and it reaches the other end at t is equal to 2, then the time period will be capital T is equal to 4 seconds, because after 2 seconds it will reach here, it will take another 2 seconds for it to come back, so at t is equal to 4 it will be back at its original position. Similarly, if I extend this object and I release it from this end, it will take some time to go to the center, then to the left end, back to the center, back to the right end. That total time will be the time period of this motion. Now that's harmonic motion. What about simple harmonic motion? Simple harmonic motion, which is abbreviated as SHM for short, is a special type of harmonic motion in which a particular equation is followed. That equation is F is equal to minus kx. There are other variations of this as well, we'll see them later, but basically this should be the form of the equation. That means if I displace the object slightly, the restoring force on it should be proportional to the displacement. There's a minus sign because it always tends to take it towards the center. That is what creates the harmonic motion. So let's start with springs and we'll move on to pendulums later on. So if I consider a one-dimensional case, I have a spring of a certain natural length and there is an object of mass m kept at its center. Let's call this point, which is the center, x is equal to 0. This is the positive direction and the left is the negative direction. So if I displace the object by a distance x, then the new length of the spring will be L0 plus x. Let's say this length is L0, which is the natural length of the spring. So initially the force that the spring applies on this block is 0 because there is no extension or compression. If I pull it towards the right a distance x, then a force will act towards the left. and that force will be equal to minus k times the extension. The extension will be x, the distance I move it. If I move it a certain amount, it will reach this place, right? So F is minus kx. This is the scalar version of the equation we just saw. Now, an important thing to note is F is equal to minus kx as applied for springs comes under Hooke's law, which we've seen earlier, which is only valid as long as x is very small. If you are extending a spring such that the new length becomes twice the original length, then Hooke's law will not be valid. Only if the extension is very small compared to the natural length, in that case Hooke's law will be valid. Another way of saying this would be, rather a more accurate way, would be x by L0 should be much less than 1. And in this chapter we'll assume that that is true. So for the cases of spring, the motion is simple harmonic if we only displace the object slightly. If the displacement is very large compared to the natural length, it will still be periodic if there is no friction, but it will not necessarily be simple harmonic. It might be something like minus k1x, minus k2x squared, or x cube, or some weird function like that, we don't know. But for small displacements, F is equal to minus kx is valid, and thus the motion is simple harmonic motion. Let's study this motion in a little bit more detail. So F is equal to minus kx gives me the acceleration is equal to minus k by mx, where m is the mass of the object. This is often written as minus omega squared x, where omega is a new variable whose value is equal to root of k by m, and it is called the angular frequency. In this chapter the terminology is slightly, a lot of it sounds the same but is different, so you need to pay attention to that. Omega is called the angular frequency. Why it's called that we'll see in a minute. Now a lot of times you'll see the equation of a simple harmonic motion written as a is equal to minus omega square x. That is to emphasize the fact that omega square will always be positive and the direction of a and x has to be negative, otherwise there will be no restoring force. If this spring was such that if I pull this object towards the right, the spring would apply a force towards the right, then any small disturbance would result in a force towards the right and the object would move towards the right forever. The only way we would have periodic motion is if I displace it towards the right, the spring pulls it towards the left, and if I displace it towards the left, the spring pushes it towards the right. Okay, so A is equal to minus omega square x is the standard equation for a simple harmonic motion. Anytime we see an equation like that, we can assume that it's simple harmonic motion. Now, A is equal to omega square x, if we know omega square or omega, does not completely categorize a simple harmonic motion. It does tell us some things about the simple harmonic motion, but it doesn't tell us, for example, where would the particle be at t is equal to 5 seconds. Right, and we've seen analogs of that in kinematics. We need what are called the initial conditions. So for example, now let's forget the spring. Let's assume this is the left end, right end and the center. If an object is moving from the left end to the center, to the right end to the center, back to the left end, then you can't really ask where the body will be at t is equal to 5 seconds unless you know where the body was at t is equal to 0 seconds. If the motion started at this point, and we know the time period, let's say, then after some time, let's say the body would be here. If it were have started somewhere else, it would have ended somewhere else. So where it starts is important. That is the first initial condition. We'll call it x0. x0 is the initial position of x. Technically, at any time it would be fine if we were known that x is equal to 4 at t is equal to 7. That would do the job as well. But we'll assume that we are given the initial x. Also, let's say I say the object starts from this point. That really doesn't tell us everything because it is at this point in two different stages of its motion. It is going from this extreme towards the center, or it touches this wall and comes back. So if it is at this point, it could have a velocity towards the left or towards the right. So just the x does not completely determine the initial conditions. For the same x, you could have different types of motion. So the second important thing, or the second initial condition, will be v0, the initial velocity. If it is towards the right, then v0 will be positive. If it is towards the left, then v0 will be negative. I mentioned that if we know the time period, this is true, and now we'll start the actual numerical analysis where we'll see that omega is directly related to the time period. So now it's pure kinematics in calculus. We have A is equal to minus omega squared x. There are many ways to try to solve this equation. The simplest way, it seems to me, is if I write A as v dv by dx. So that gives me v dv is equal to minus omega square x dx. Now we'll integrate it, and let's say at time t is equal to 0 it was at x naught, at time t is equal to 0 the velocity was v naught, at a particular time it is x and it is v. So the equation we get is v square by 2 minus v naught squared by 2 is equal to minus omega squared times x squared by 2 minus x naught squared by 2, or I'll just put the minus sign inside now. So that gives me v naught squared by 2 plus omega squared x naught squared by 2 is equal to v squared by 2 plus omega squared x squared by 2. Now that gives me an important relation: v squared plus omega squared x squared is equal to v naught squared plus omega square x naught square. And this is value for all v and x. So we basically found a quantity that is a constant, right? And it will become clear exactly later why we've chosen this particular value. But this particular constant, we'll call it omega squared a squared. Again, we needed a new value. We could have called it a, but a would not really have any practical significance. If we call it omega square a squared, we'll see that a will end up having some practical significance. We've just introduced a new constant. Why I'm choosing this will be clear in a minute. So omega is something we already know. So we've created this particular new value and we'll call it omega square a squared. Right. So from this we get the equation v is equal to omega root of a squared minus x squared. Right. Now we can use this and say this is equal to dx by dt to get the actual equation of trajectory, which would be x as a function of time. Sorry, this should be dt. You see that we've basically, other than the simple harmonic motion part, we've not learned anything new in this chapter except the equation a is equal to minus omega square x. After that, we're just proceeding like we do in any kinematic equation. So this is equal to dx by dt, which gives me dx by root of a squared minus x squared is equal to omega dt. Now root of a squared minus x squared has an integral sine inverse x by a. So this will give me, if I put the limits as, let's say this is 0 and t, initially t is equal to 0, it was at x naught, finally it's at x, so it will give me sine inverse x by a minus sine inverse, this is capital A, x naught by a is equal to omega t. Now again, sine inverse x naught by a is just another constant. We'll label this constant as delta. Right. So from this we get the equation omega t plus delta is sine inverse x by a. That gives me the equation x is equal to a sine omega t plus delta. And from this equation, hopefully you can see why we chose this particular thing to be delta and this thing to be omega squared a squared. So this is the solution to this problem. This is the problem. This is the solution. Given that at t is equal to 0, x was x naught and v was v naught. We would ideally write this as this particular thing and delta as this, but this is just for the sake of clarity. So this derivation is important. I hope it's clear to you. We'll see the same thing again and again in different contexts, so I'm not going to derive it again. So if you have any trouble, look at it once again. This is quite important. How we got from a is equal to minus omega square x to x is equal to a sine omega t plus delta. Anytime this is the equation of motion, this is the basically the force equation, F is equal to minus kx. Anytime that is true, this will be the motion. The only things which would be different are a and delta depending on, a and delta depending on what x naught and v naught would be, what the initial conditions would be, whether I initially leave it at the center or leave it at one extreme position or somewhere in the middle. Right. So now let's look at this particular equation in more detail. X is equal to a sine of omega t plus delta. So for a second, let's assume delta is equal to 0. Let's assume it is a sine omega t. What that says is that if this is x is equal to 0, the particle was here initially. Then it reached x is equal to capital A after some time. What was that time? When this will be pi by 2. So this will be at t is equal to pi by 2 omega. Then it reaches the origin back again, and then it reaches this particular left extreme where x will be minus a. And when will that be? When this is 3 pi by 2. So at that time t will be 3 pi by 2 omega. And then it will reach back to its origin. And when will that be? When this particular thing becomes 2 pi. See, x is equal to 0 at 2 points. After 0, omega t could be pi. That means it's gone to one extreme and come back. That's not a complete motion. That's just half of motion. Then it goes to the other extreme and comes back. That completes the motion. And when will that happen? That will happen at time t is equal to, this has to be 2 pi. This is 2 pi by omega. And that is capital T, our time period. Right, because that is the time after which the motion repeats itself. If you started from one extreme, after time 2 pi by omega, it would reach the other extreme. In fact, from any position, because if the time shifts by 2 pi by omega, then omega t will shift by 2 pi. And if omega t shifts by 2 pi, we know the value of the sine function does not change, so x will be the same position. Now you also see why we chose that particular quantity to be omega square a square as opposed to a, because now a has a special significance. A is called the amplitude of the motion. Amplitude of the SHM. Amplitude is basically the maximum extreme position it goes to. So if the SHM has an amplitude of 5 meters, that means it goes 5 meters to this end, comes back, 5 meters to the other end, comes back. Right. You can also see now why omega is called the angular frequency, because it is the frequency of the change of the angle. Another important quantity, mu, is the frequency. That is simply 1 by t. Sorry, frequency. Omega is 2 pi by t and mu is 1 by t. So mu is the frequency. In practical terms, mu would be the number of oscillations taking place per second. Omega would be the frequency of change of radians. So they are related by a factor of 2 pi, because one whole oscillation is a change of 2 pi radians. Finally, let's go to delta. In this case, if this is the equation, then there is no particular initial condition other than the fact that it is at t, x is equal to 0 at t is equal to 0. But if we add a delta, then that delta would change a lot of things. If that delta was pi by 2, then it started at this extreme position. If that delta was 3 pi by 2, then it started at this extreme position. So delta relates to the initial condition, and if delta is 0, that means it started at the origin, but if delta is something else, that means it started somewhere else. Also, we could always change delta by a factor of pi by 2, and this would become a cos omega t dash. This is the same equation, except now it will be some other delta. So we see that there are many physical quantities associated with the SHM, but there are three quantities which characterize the SHM. The first is omega, which is decided by the mass of the object and the spring constant. They both together root k by m give us omega. The second is a, which decides the amplitude of the motion, and the third is delta, which is related to the initial condition. If delta is 0, it is initially at the origin. If delta is some other value, it's somewhere else. So these three things characterize a simple harmonic motion. Let's see a few other things about the simple harmonic motion. We have now x is equal to a sine of omega t plus delta. That gives me v is equal to the derivative of this, which is a omega cos omega t plus delta, right? And this does work for the simple case of delta is equal to 0. So let's assume delta was 0, it was initially at the origin. right? At that point, what was V? If delta was 0, V is A omega. That is its maximum value. And we know that at the center it has its maximum value. As it moves forward, V decreases, and when it is at the end, at that time T is equal to pi by 2 omega, and if delta is 0, this will become cos of pi by 2, which is 0. So here V is equal to A omega, that is the maximum possible value. Here V is equal to 0. Then it comes back, and at that point it will be 3 pi by 2 omega. Cos of 3 pi by 2 will be minus 1. So this will give me minus A omega. Sorry, cos of pi, right? Minus A omega. And this point will be minus, sorry, it will be 0 again, because cos of 3 pi by 2 here will be 0. So if we know x as a function of t, we can find out v as a function of t. That's something we already knew. A will be dv by dt. So there will be another omega, and it will be sine, and there will be a minus sign. So it will be minus omega square a sine of omega t plus delta. And no surprise, this is actually equal to minus omega square x. So we see that if a is minus omega square x, then this is the general form of the equation that will follow. What is the kinetic energy at any point of time? That will be half mv square, that will be half m omega square a square cos squared omega t plus delta. What is the potential energy in the spring? We know that is equal to half kx square at any point. So that will be equal to half k a square sine square omega t plus delta. And we knew that omega is equal to root k by m, omega square is equal to k by m. So m omega square is equal to k. I'll just write it as m omega square as well, since they're the same thing. That gives me the total energy is half m omega squared a squared, since sine square plus cos square theta becomes 1. And this is important. It tells us that the total energy in a simple harmonic motion is always conserved. It just keeps changing from kinetic energy to potential energy. When it is at the center, then the speed is maximum. It is all kinetic energy, no potential energy. Because x is 0, the spring has no potential energy in it. When it is at the extreme points, this point or this point, then the kinetic energy is 0, because there is no speed of the object. It is at rest, instantaneous rest. But the potential energy is maximum, because there is maximum extension or compression. And so what is the maximum value of kinetic energy? When this would be 1, that is half m omega square a squared. What is the maximum value of potential energy? When this would be 1, that is half m omega squared a squared. So the sum of them is always half m omega squared a squared, and at the extreme values kinetic energy is 0, and at the origin the potential energy is 0. Yeah, so this completes linear SHM. Now I'm not going to show you some examples of problems. They're simple enough. Once you understand this concept of if a is minus omega square x, then the equation will be x is a sine omega t plus delta. Let's move on to pendulum now. How does pendulum relate to simple harmonic motion? So there are many forms of simple harmonic motion. What we've been seeing up till now is actually linear simple harmonic motion. And now we'll see a new type, that is angular simple harmonic motion. Okay. So what will happen if we tilt this by an amount theta? Right now this object is at rest because there is mg acting downwards and tension acting upwards, which will balance each other. At this point it can't be at rest. Mg is acting downwards and tension is acting in this direction, right? So when we're talking about circular motion, we always do it along and perpendicular to the radius. So this angle will be theta. That means this will be theta. That means the component in this direction will be mg sine theta, and in this direction will be mg cos theta. Mg cos theta will not cause any torque. Mg sine theta will cause a restoring torque. Now we've seen linear motion and we've seen circular motion, and we saw that it was completely analogous. We had F is equal to ma, we had torque is equal to I alpha, right? We had momentum is equal to mv, we had angular momentum is equal to I omega. So it was completely analogous. Similarly, in a linear SHM we have a restoring force. In angular SHM we have a restoring torque. And what will that torque be? That will be mg sine theta multiplied by this length of the string, that will be L. So the torque is mgl sine theta. That is equal to I alpha. Actually, it's minus mgl sine theta because if theta is positive, it's towards the left, right? What is I? I will be ml square because we are considering a simple pendulum in which the rope is light and there is a small bob at the end. So minus mgl sine theta is equal to ml squared alpha. So 1l cancels, cancel, and what we get is alpha is equal to minus g by l sine theta. Again, if we want to make it look like that, we'll define g by l as omega squared, or omega is root of g by l. That gives me alpha is minus omega squared sine theta. This is not quite the equation for simple harmonic motion, but we do know from mathematics that if theta is very small, then this is equal to minus omega squared theta, because sine theta is approximately equal to theta for small values of theta. So angular SHM only happens when theta is small. This is an analog of linear SHM. We know that for a spring, it's always periodic motion, but it is simple harmonic motion. That means F is equal to minus kx only if x is much smaller than L. Similarly, angular simple harmonic motion is only that if theta is very small. So we see a general pattern that even though motions can be periodic, simple harmonic motion, that is that specific sinusoidal motion in which x follows a sine theta, that only happens for small disturbances, and this is a pattern which you'll see throughout physics. So now we see the beauty of mathematics as it relates to physics. Once we have alpha is equal to minus omega square theta, we know everything else because the relations are the same, right? The angular velocity will be d theta by dt, the angular acceleration will be d2 theta by dt squared, and we'll solve it and it will come in exactly the same way. So the final answer will come out to be theta is equal to theta naught sine of omega t plus delta, where theta naught is called, you guessed it, the angular amplitude. And omega is root of g by l, and the time period is 2 pi by omega, that is 2 pi root of l by g. I'm sure you've seen this result before. Now finally you've been able to derive it. So the time period of a simple pendulum is 2 pi root l by g. A couple of important things for the simple pendulum. Kinetic energy in this case will be half I omega squared. Now a little bit of problem occurs at this place because we are using 2 omega. So what I'm going to do is I'm going to use the capital Greek omega, which is this. So this omega will be d theta by dt, which is the angular velocity, and this omega is the angular frequency. Which is root of g by l. So don't get confused between the two, right? So it'll be, I'm just saying that because usually when we write half I omega square, we use this particular symbol. So omega will be d theta by dt. If theta is theta naught sine omega t plus delta, then omega will be theta naught omega cos of omega t plus delta. It will be d theta by dt. Right? So this gives me half I omega square theta naught square cos square omega t plus delta. This is the kinetic energy. What is the potential energy? Potential energy in this case will be, just like it was half kx square for the case of a spring, it will be half k theta squared, and that will be half I omega squared theta naught squared sine squared omega t plus delta, and that gives me the total energy, which is a constant, half I omega squared theta naught squared. Right. So we see that just like we had circular motion and linear motion, circular angular SHM and linear SHMs are very analogous, with just the terms, symbols meaning different things. Finally, there is one more small thing called the physical pendulum. And in that case, earlier we had a simple pendulum where we had a rope and a bob was attached to the end. But if we have some random object which does not have a particular specific shape, then also if it had a particular center and we shifted it towards the right, it would end up oscillating, and in fact it would end up oscillating as simple harmonic motion. So in that case the equation would be torque, which is again minus mg L sine theta. In this case L would be the distance of the center of mass from the origin, which at rest would be, this line would be completely vertical. So torque is minus mg L sine theta, that will be equal to I alpha. Now from this, in the previous step we proceeded to put I is equal to ml square, but in this case we don't know what the I is. So let's just leave I as that, and we can do it for many specific objects. For example, we could do it for a rod, or a rod with another vertical rod attached to it at the end. So from this you get the equation that the time period, instead of 2 pi root L by G, is 2 pi root of I by mgl. 2 pi by omega, basically omega is root of mgl by I. So for the simple pendulum it's 2 pi root of L by G, and for the physical pendulum it is 2 pi root of I by mgl. We can see that if I put I is equal to ml square, then it becomes 2 pi root L by G. This completes basic simple harmonic motion. We'll have another video on simple harmonic motion where we'll discuss some advanced concepts. Thank you.